Example 10.16. The statement of example I have discussed in the slides, and this is the same example. Okay, 8-story building, base or the ground floor, first, second, third, fourth, fifth, seventh, eighth. Okay, so there are 8-story building, RC frame, which is to be built in Ahmedabad. The columns are 4 meters center to center to the plane of the paper. Okay, this spacing is 8 meter, and the perpendicular to this 8 meter is 4 meter spacing column to column. Determine the earthquake base shear and its distribution over each story level, considering floor finish equal to 200 kg per meter square. Mean floor finish on each floor is 200 kg per meter square, and partition load of 100 kg per meter square. Outside walls are assumed to have a mass distributed over the plan area 300 kg per meter square. On each floor, the outside wall load is 300 kg per meter square except for the top roof. For the top roof, the outside wall load is 175 kg per meter square. Slab thickness for floor 1 and 2, that is 200 millimeter, and the for rest of floors, that is 150 millimeter. Okay, first of all, the building is to be will be built in Ahmedabad. So we have to find from the maps, from the building code of Pakistan, or if the city or in any country in Saudi Arabia or any other country. So in America you can see the UBC graphs, okay, UBC tables, or depending upon your city, you can find the zone factor. Okay, now Ahmedabad city, according to building code of Pakistan 2007, consider the given part of the Ahmedabad to be placed in zone 2b for the present example. Okay, so selected that this city is lie in the zone 2b. The soil profile type may be assumed to be SE. Okay, for zone 3 and zone 4 you can select SD, and for others you can select SE. Okay, this is the assumed value. Okay, now the total height of the building 433. Okay, the total height of the building is 25 meter, and for the concrete building the CT factor is 0.073 as per UBC 97A method. Okay, you can also see here CTHN. CT is 0.073, HN is the height of the building excluding parapet. So here is the formula time period of this building, 0.073 multiplied by 25 power 3 by 4. The time period of this building is 0.816 second. Okay, now the load of or weight of first floor and second floor. Okay, the thickness is same 200 millimeter, so 0.2 into unit weight 2400 kg per meter cube or density plus 100 plus 100 is the partition load, 200 is the floor finish load, and 300 is the outside wall load. Multiply by 8 into 4. It is the floor dimension 8 meter in this direction, other direction 4 meter. Okay, to calculate the total load of the story. Multiply by 9.81 divided by 1000. Okay, the first and second story weight is 339 kilonewton. Okay, you can also verify by your calculator. Now for 3, 4, 5, 6, 7. Okay, the slab thickness is 150 millimeter, and the rest of the loading is same 0.15 2400 plus 100 plus 200 plus 300. Okay, move partition load floor finish load and outside wall load, multiply by area of the floor 8 by 4 meter, to convert into kilonewton 9.81 divided by 1000. So that is the weight of for the third floor, fourth floor, sixth floor, seventh. Now the eighth floor, only the difference is this: there is the outside wall load not 300, that is 175 kg per meter square. So that's I have put here. Now multiply by area of the floor, multiply by 9.81 divided by 1000. Okay, now the total load of the building, or the total seismic weight. Okay, that is I have discussed in the slides, total seismic weight. Seismic weight will include dead load of the structure, 25% floor finish, okay, live load for floor live load for storage, a minimum allowable of movable partition 50, the total weight of permanent fitting. In this example, the total weight of permanent fitting is not allowable, not present, so these values are skippable. Even the movable partitions are also not there. We are calculating only the dead load of the structure. If any of these are present, depending upon the condition, you have to also consider in the total seismic weight. So now total seismic weight 2 times 339, because 2 stories, first and second, that is 339. Now from 3 to 7, there are 5 stories, 5 into 301.4, and the last story is single, that is 230.7. So the total seismic load, that is 2415.7 kilonewton. Okay, now the zone is 2B and soil profile type is SC. Okay, here if you know the zone type and soil profile type, zone type is zone 2B and soil profile type is SE, then you have to pick the factors, these two factors for CA and CV, 0.34 and 0.64. Here 0.34 and 0.64. Okay, now I is 1.25. Okay, because why 1.25 and 8-story hospital building? Because that is essential and important building. For example, if an earthquake happens, then if any building destroyed, but a hospital building should not be destroyed, because this is the last shelter for the people, for the patients. So that's why it is an important building. So the importance factor, that is 1.25. The time period of the building, that we have calculated already, 0.8116 second. And response modification factor, that is 8.5 if special moment resisting frame is designed. If the detailing now it's the initial forces stage, after designing of the members, if we do the special moment detailing, then the R value 8.5 should be picked. Okay, our RC frame, so that's why response modification factor, steel or concrete special moment resisting frame, R value is 8.5. Okay, now to calculate the base shear coefficient, okay, base shear coefficient or seismic shear coefficient, so all these names are of this CS. So that is uh, CS is equal, let me open the slide for the base shear seismic shear coefficient. Here for response time, CV over 2 points CA, and TA is 0.2 times of TS. Okay, so here is TS 0.64 CV over 0.34 multiplied by 2.5, the value is 0.753 second, and 0.2 times of TS is TA. Okay, so now the CS is CV I over RT. CV is seismic velocity base coefficient, I is the importance factor, R is the response modification factor, T is the time period of the building. So CV is 0.64, I is the 1.25 and divided by 8.5 and the time period 0.816. The seismic shear coefficient is 0.1153. Okay, now we have to check against minimum and maximum values. The minimum value of CS is 0.11 CAI. So CA is already we have, I is the importance factor, so that's it. Okay, so our TA is greater than TS, sorry, our as TA here, that is here, time period by A method. So our T is greater than TS. So here CS, if our time period of building here TA, that is capital A, or TA is greater than TS, then subject to maximum and minimum values. Minimum values we have checked. Now for maximum values, okay, 2.5 multiplied by CA 0.34 multiplied by 1.25 divided by 8.5. The value is 0.15. Okay, so the maximum value is 0.15, that is our CS is less than maximum value, so that is also okay, and it is also greater than minimum value, so that is also okay. Hence CS value will be 0.1153. Okay, then how to calculate the base shear? Base shear formula is V is equal to CSW. Okay, CS is the seismic shear coefficient and W is the total weight of the building. So the base shear value is 278.5 kilonewton. Okay, what is this base shear? The total weight of the building which will act as a horizontal earthquake force or a horizontal base shear. Okay, that is the value is 278.5 kilonewton. Now this value need to be distributed upon each floor. Okay, now the force will transfer from the base to the one by one in each story. Okay, so now the third another condition is also meeting here. If the if your time period of the structure is greater than 0.7 second, then in the higher modes, then the to accommodate the higher modes of vibration, you need to consider additional FT force at top. Okay, so here we also need to cover that force, so that is the same formula. Now for FT the formula is 0.07 time period into base shear. Okay, the value is 15.9 kilonewton if the time period of the building is greater than 0.7 second. As time period of our building is greater than 0.7 second, so we will consider this FT force. Okay, so this is the formula I have promised in the slides. I will discuss in the example this formula. So now that is much better circumstance that I will discuss this formula. Okay, here V value is 278.5 and FT value is that is 278 point FT value is 15.9 and base shear value is 278.5. Now this base shear we have to distribute in each floor level. The value of lateral forces at various levels are calculated in table 10.13 and are graphically shown in 10.52. The force Ft in this figure accounts for the effects of higher modes of vibration. Okay, we have calculated 15.9 when time period is greater than 0.7 second. So now see, here is the table calculation for lateral forces, for example 10.15, sorry 10 point, that is wrongly written 10.16 not 10.15. So now in the table you can see level. There are 8-story building, 1, 2, 3, 4, 5, 6, 7, 8, and first story weight is 339, and second, third you can also check. Okay, first story, second story 339, and the third, fourth, fifth, sixth, 7, 301, and the last 230.7. So same here, the weights of each floor is present here. Now the height of the building from the base. Okay, the first floor height is 4 meter, and the second floor height is 7 meter from the base of the building. Okay, here first floor height is 4 meter, and the second floor height is 3 plus 7 3 plus 4 7 meter, and the third story height is 10 meter. Okay, so that's how hx value from base from the base have been put it. The total height of the building 25. By adding each story height, the 8-story height is 25 meter. Now you will multiply the each story weight to its story height. Okay, 230.7 multiplied by 25 here, 301.4 into 22. You can also verify. 301.4 multiplied by 22. Okay, 6630.8. Okay, kilonewton meter. Okay, so at the end you have did the summation or sum of all the wx hx, that is 33608.5. so that is wi hi, the sum of all these moment values, load into moment values. Okay, kilonewton meter, so 33608.5. and for the individual story, for each story wx and hx, that is written here. Okay, now for the first story, okay, you will put this 1356. Okay, now for the first floor base shear calculations. Okay, here in the formula I will put the values as it is. Okay, that is 278, and let me okay, the base shear is 278.5 minus ft is 15.9. okay, multiply by wx hx of that story, that is 1356. okay, now under the bracket, that is total wx hx total summation values, that is 33608.5. okay, I will put equal, the value is 10.56. okay, the rounded value is 10.6. similarly for each floor, v minus ft into wx hx divided by total. okay, for each floor, after doing the each floor, the in the top floor you need to add ft values. You have to plus the ft values. Why? To consider the force ft in this figure accounts for the effects of the higher modes of vibrations. So here, okay, for this story, 5767.5. okay, I will put equal, the value is 45.064, 45.1. okay, plus ft, that is 15.9. okay, so this is the total value at the top floor. okay, so now this distribution can be seen in the graphical form. okay, here The story shear in the first floor, that is 10.6, similarly 18.5, and then it is increasing. The at the top only Ft will be added, will be plussed only in the top floor to account for the higher modes of vibration. Okay, so that is 61. So this 61, now we have to accumulate, make the cumulative of these all values. 61 plus 51.8 plus 51.8, that is 112.76, you can say 8, then plus 44.7, that will be 157.5. okay, similarly you have to make the cumulative 37.7 and make this cumulative story shear. Okay, why we did the cumulative? If any force comes in the 8th floor, okay, then the lower floor should have also the capacity to resist that force. Okay, for example, if the lower floor do not have the capacity, the force is more in the upper floor, then lower floor will fail. So the lower floor should also have more capacity than the upper floor, similarly downwards. Okay, so that's why we have to design the lower floor for the value of 278.4. Similarly, for this floor, second, 267.8. Similarly, going up, we need to design our members according to this cumulative story shear. Okay, so that's why it can resist the forces in the upper floors. So that's the individual and cumulative story shear, for example 10.16. So that's all for today's lecture, and this is a good example. And at the end of this chapter there is an example you have to also do as an assignment. Okay, so that's all. Have a nice day.